By now you're probably used to the idea that theorems tend to come in clusters, and that the purpose of some theorems is to prepare the ground and get preliminary results for more important theorems that are going to be applied later in other parts of mathematics. And sometimes one of the difficulties in learning mathematics is that the particular theorem you're studying, you're not quite sure of the status of the theorem. You're not quite sure what its purpose is. So what I want to do today is to try to give you some feel for the geography of the work on Taylor series, to help you find your way through the chains of theorems that you'll meet when you're studying Taylor series in Unit 6. First of all, we'll look at real power series and see how they can be generalized to complex power series and how they can be used to define analytic functions. You see, earlier in the course, we've proved a lot of interesting and sometimes quite surprising results about analytic functions. There are lots more results like these about analytic functions. But so far in the course, we haven't seen very many analytic functions, and if there aren't many, then these theorems, for all their elegance, wouldn't be very useful. And not all the functions we use in real analysis can be generalized to complex analytic functions. In real analysis, you can differentiate the modulus function everywhere, except at just one point, at 0. But the complex modulus function is rather different. We saw earlier in the course that it's not analytic. If we couldn't extend other real functions to include complex numbers, we might be in trouble. We can solve this problem using power series. The three theorems we're going to prove tell us about where a power series converges, that the function it defines is analytic, and that you can construct complex analytic functions by generalizing real power series. So let's start then by looking at a power series. It's just like real analysis, except that Z can take complex values. The general term for the series is this. This power series is centered at alpha, but for the moment we'll concentrate on power series centered at 0. The proofs generalize very easily. At those values of Z where the series converges, it defines a number, fz, and the set of those values of Z will be the domain of a function f. So our first theorem asks what these domains look like. Just what kind of sets do power series converge on? In fact, the sets are very simple. They're disks. And to prove this, we use a lemma. If we have a point Z0 where the series converges, we'd expect it would also converge for values of Z nearer the origin. So what we prove is this. If a series converges at Z0, then it converges at any point Z where the modulus of Z is less than the modulus of Z0. It converges at all points in the open disk. We're not going to prove that here, because although the proof is technically complicated, it's not particularly subtle. We want to use it to prove that power series must converge on disks. First, we'll exclude two special cases. It's possible for a power series to converge everywhere, and you can imagine that as an infinitely large disk. Or it might converge at only one point, a disk of 0 radius, if you like. And let's put these two special cases aside. Now we'll take a circle and suppose the series converges everywhere inside it. We'll call a circle like this a C circle. C for converges. And we'll draw it in white. Now we'll take a larger circle and suppose the series diverges everywhere outside it. We'll call that a D circle. Now look at the C circle. Inside this circle, the series converges. So any smaller circle inside it must also be a C circle. In the same way, we can take the D circle. Any larger circle outside it must also be a D circle. The question is, can there be a gap? Or must every circle be a C circle, or a D circle, or possibly both? If there's no gap, there must be a circle which, in a sense, is the boundary of the C circles and of the D circles. We'll try to find that boundary circle by looking at the smallest D circle. We'll call it DL. It's just the greatest lower bound of all the D circles. Now, draw a circle inside DL. Is it a C circle, or a D circle, or perhaps is it neither? Well, we know it's not a D circle, because DL was the smallest one. So what does that tell us? It tells us there's a Z0 outside S where the series doesn't diverge. In other words, we've got convergence at some point Z0 outside S. Now we can use our lemma. The series converges at Z0, so it must converge at all points nearer the origin. And any point inside the circle S is nearer the origin than Z0, so the series converges everywhere inside S. That means S is a C circle. But remember, S was any circle inside DL. So DL is also the largest C circle. So we've found a circle which is the boundary of the C circles and the D circles. We call it the circle of convergence. The series converges at all points inside the circle and diverges outside. What happens on the circle we can't say. It just varies from case to case, and we have to check each one separately. So that's our first theorem. Before we move on, let's just compare this result with real analysis. Real power series converge on intervals. For example, take 1 over 1 plus x squared for real x. Its power series converges from mod x less than 1, x lying between -1 and +1. It converges on an interval. But if we allow complex numbers and look at 1 over 1 plus z squared, we get this power series just by replacing x for z, and this series converges on a disk. So now we know the kind of sets that power series converge on. They converge on disks. But are the functions defined in this way analytic? We hope they will be, and we could check by showing that you can differentiate them, that this expression has a limit. But fz is defined by a series, so it's really quite a performance. We'll try a different way. We'll use a test for analytic functions. We'll use Morera's theorem. This theorem was proved in Unit 5. that says that if you have a function defined on a region, and if for any triangle completely in that region the integral around the triangle is 0, then on that region f is analytic. So we'll use Moreira's theorem to prove that our function is analytic. But to get started, we must first of all prove that we can integrate f. And we can do this if f is continuous. Now, to prove continuity, we do appeal to the definition. The proof is in the text. And having proved continuity, we know that we can integrate f. But we don't yet know how to calculate the integral. After all, f is defined by an infinite series. So let's look at the partial sums. Then fz is the limit of fnz. We've left a space so that we can integrate both sides. The integral of fz along any contour gamma is the integral of the limit of fnz. And in the text, we prove that we can interchange the order of the integral and the limit operations. Now, suppose gamma is a triangle. Then for any n, the integral of fn around gamma is 0. And that's just by using Cauchy's theorem, because fn is just a polynomial. So the limit of the integrals must also be 0, and therefore the integral of f must be 0. In particular, the integral around any triangle within the circle of convergence is 0. So f is analytic on the whole open disk. So a function defined by a power series is analytic on the open disk bounded by the circle of convergence. And so it has all the nice properties we've come to associate with analytic functions. Our final theorem is going to be about extending real functions to complex functions. But before we can tackle it, we'll need to say something about Taylor series. Every analytic function can be expressed as a Taylor series. It's very similar to the Taylor series you get in real analysis. This is the general form centered at alpha. You can also have a finite form of the series. You just take the sum up to n-1 and then add on a remainder term involving a function, gn. And the value of gn at alpha is given by this formula. We prove in the text that gn is analytic throughout the domain of f, even at points where the Taylor series might not converge. Now we're going to use these two forms of Taylor series to prove our final result about extending real functions to become complex functions. Earlier in the course, we defined the complex exponential function like this. But we could have tried another approach. We could have started with the real exponential function and its Taylor series. Then we could have just changed x to z in the series. But of course, this approach raises problems. First, does the complex power series converge? We're now able to answer that. It does. But there's another, more difficult question. Does the power series give a proper definition of the complex exponential function? By proper, I mean this. Can there be another function g which is not the same as the exponential function in general, but which has the same Taylor series on the real axis? You see, we might have two functions which weren't the same but just happened to to coincide on the real axis. And if that were the case, we might not be able to generalize the real Taylor expansion to give us the appropriate complex function. To find an answer to this problem, let's put it a little more generally. If the two functions are equal on the real line, then does it follow that they are equal throughout C? The answer, as we'll see in a moment, is yes, provided they are analytic on C. Now we can simplify the problem a little. Instead of writing fx equals gx, we can write fx minus gx equals 0. And similarly, fz minus gz equals 0. So if we give a name to the function f minus g, call it h, then the question we're asking is this. If h is an analytic function which is 0 on the real line, must it be 0 everywhere? We answer this question by showing that for any analytic function h, there are only two possibilities. Either an analytic function is 0 everywhere, this is the case we want, or else any point where the function is 0 is an isolated point. By isolated, we just mean this. If h alpha is 0, then we say that alpha is a 0 of the function h. It's an isolated 0 if we can find a neighbourhood of alpha where the function never vanishes, except, of course, at alpha itself. Now, if we know that h is 0 all along the real axis, then any 0 on the real axis is not isolated. And if the zeros aren't isolated, then the function must be 0 everywhere. So we'll have proved our result if we can show that these two alternatives must be the only possibilities for an analytic function h. And we do this by supposing h is 0 at some point alpha. If this is so, you might expect to be able to take out a factor z minus alpha and write this, where g is some other function. And you might be able to take out several factors. And if you can't take out more than n factors, we say that alpha is a 0 of order n. And then g alpha must be non-zero. Now, can we use this to tell us that the zeros of h are isolated? We can if g is continuous, because g is non-zero at alpha. And if it's continuous, it's also non-zero on a neighbourhood of alpha. And z minus alpha is also non-zero on this neighbourhood, except at alpha itself. So the product, hz, is non-zero on the punctured neighbourhood, so alpha must be an isolated 0. So let's gather together the threads we've got so far. Suppose alpha is a 0 of h. If we can express h in this form, where g is continuous, then we'll know that alpha is an isolated 0. The proof that we can do this comes from the finite form of Taylor's theorem. If the first n-1 derivatives of h are 0 at alpha, and the nth derivative is not 0, then we choose this form of the expansion. The first part vanishes because all the derivatives in it are 0. And the second part is in just the form that we want. We know that Gn alpha is non-zero because the nth derivative of h is non-zero. And we also know that Gn is analytic, and so it has to be continuous. So if the nth derivative of h is the first non-zero derivative, then Gn is just the function we want. And the 0 at alpha will be an isolated 0. There's only one other possibility. All the derivatives might be 0, and then we wouldn't be able to find a function Gn. But we can see what happens by looking at the other form of Taylor series, the infinite form. If all the derivatives are 0, then the function must be 0 everywhere. And that was the other possibility that we wanted. So let's summarize the argument. If all the derivatives of h are 0, then hz is 0 everywhere. If, on the other hand, the nth derivative at alpha is non-zero for some value of n, then we've seen that alpha is an isolated 0. And in this way we can show that all the zeros will be isolated. But now, let's go back to our original problem. We were assuming that hx was 0 for all real values of x. So the zeros of this function cannot be isolated, and the function must be 0 everywhere. And now we can go back to the definition of the function h. It's just the difference between two functions. And what we've proved is that if the functions are equal on the real line, and that is the difference function h is 0 there, then they must be equal everywhere. So we can use definitions like these for complex functions. We know the series converge, and since they reduce to the real Taylor expansions on the real line, we can use them as valid generalizations of the real exponential and trigonometric functions to complex variables. So if two functions coincide on the real line and they're analytic throughout the complex plane, then we know that they must coincide throughout the complex plane. Now in the text, we generalize this result a little. Instead of requiring that they coincide on the real line, we require that they coincide on some more general set. And then we prove that if they're analytic on a region containing that set, then they must coincide throughout that region. Now that raises a small problem because it may turn out that the Taylor series doesn't converge throughout the region. It might not be a disk, for example. So what you have to do is to use the finite form of Taylor series, but with a remainder. And you use the fact that although the Taylor series may not converge throughout the region, you know that the remainder is analytic throughout the region. Well, you'll see how that's done when you look at the correspondence text.